As the pressurized fluid in our rocket is expelled, this creates an equal and opposite reaction known as thrust. This thrust is what propels our rocket up into the air. We have found that a low water fraction does not have enough thrust to initially take off, while a high water fraction results in the rocket not being able to achieve a large enough acceleration.
Impulse is used to describe the effect of a force over a period of time and is calculated by the force times by the change in time. This means instead of looking at a specific moment in time, we can take into account how the force has changed during the entire flight of the rocket.
Looking at our results, while 0.8 had the highest impulse, between 0.4 and 0.5 we had the longest flight time. This shows us that we have to consider many factors when choosing our water fraction.
Directional stability is the ability for a rocket to be able to return to its original flight path after a disturbance. For a rocket to achieve directional stability, the centre of pressure must be behind the centre of mass. By having the fins closer to the back of the rocket, this moves the centre of pressure and helps to keep the rocket stable.
The area of the fins also affects the stability of the rocket. If the fins are too small, the force is too small to stabilise the rocket, but if the fins are too large, this can cause excess drag, which may destabilise the rocket. Therefore, we have to use an area between these 2 points that will keep our rocket directionally stable.
As we change the diameter of our parachutes, we can see that the larger the area of the parachute, the lower the terminal velocity and therefore a higher flight time. However, having a large parachute could result in the parachute getting stuck and may take longer to deploy. Taking these factors into account, we have decided to use a diameter of 0.8 meters for our parachute.
Here we have a rocket. As it is falling, it will experience an acceleration due to gravity. This will cause a subsequent drag force that is proportional to the velocity squared. As the rocket continues to fall, these two opposite forces will eventually reach a point where they are equal and max velocity has been reached. This max velocity is known as the terminal velocity.
By simulating each part of the rocket separately, we have achieved the optimal results for each section of the rocket. However, most of these results were under optimum condition and had very little interaction with other factors.
One such factor is the build quality. If the rocket is not symmetrical, this will shift the centre of mass and can cause the rocket to go sideways. We can see how a lower build quality means the rocket is more likely to go sideways during boost phase.
Another factor would be the weather, as having different wind speeds will affect the forces that are acting on our rocket. This can cause the rocket to go off from its desired flight course and affect the overall flight time.
Teamwork was a massive part to our team's success, as this allowed us to complete multiple tasks efficiently. We also learned how to communicate with each other effectively. Simulation optimization meant that when we were deciding on the design for our rocket, we were confident as a team that it had the best chance of succeeding.